Okay, this is tutorial week 3, term 4, and I'm just going to go over the exercise on page 96 of the Engineering Studies workbook, and it asks you to determine the forces in the members of this truss, where you have a 250 kilonewton force acting at that joint and a 65 kilonewton force acting at that joint there. And I'm going to show you two methods of doing this. Both methods are the method of joints. So I'm going to show you individual force diagrams here, and then I'm going to show you putting them all on the same diagram, which is a bit complex, and that's the Maxwell diagram. And the reason I'm going to show you the Maxwell diagram is because this is probably the best way of doing your model truss, which is assessment task number 1. But as I said, you'll never be asked to use the Maxwell diagram. You will never be asked to do any question in any particular way. So let's start with individual diagrams here. Now, I always use Bow's notation because Bow developed this notation because when you have internal reactive forces on a member, so this member here is AE relative to that joint, but relative to that joint, it's EA. Now, I'll just explain Bow's notation. Bow's notation is that happens when you put a capital letter between two forces and you go in a clockwise direction. So this is A, and I'll put A, and it doesn't matter where you start, by the way. So I'll put A between RL and the 250 Newton force, and I'm going clockwise. And then B is between 250 and that force. So B is all that area out here. C is between that force and that force. D between that force and the left reaction. And then E is, we're going into the truss now, F and G there. Now, the advantage of using Bow's notation is that you can analyze each joint, and the sense, because the sense changes from this joint to that joint, the Bow's notation changes. So let's just have a look at this, and I'll just draw this. So you can see here that from this diagram, the sense is going down towards the joint here. So I'm going to just put those, and I'll analyze this in a minute and explain it. And so therefore the sense will be going out there like that. Now, from previous lessons, you know that the force here is actually pushing into the joint. And the way that I get my students to figure that out is to put your fist on that joint there with a pencil in your fist and push on the pencil, and you'll see that that will be in compression. Even though you've got two forces pulling apart there, you think, oh, this is in tension. But these are internal reactive forces on the members. And so that's the best way of doing it. So you put a force going towards the joint, put your fist at the joint, put a pencil in your fist and push the direction that that's saying, and you'll see that the pencil will be in compression, so therefore that member is in compression. Now see this one here is tension. And so with tension, it will be pulling away from the joint there, and this has to be equal and opposite because the member's in equilibrium. And so put your fist on this joint here, put a pencil in your fist and do what that tells you, pull it away, and you can see that the pencil is in tension, so that whole member is in tension. Or the other way you can do it, that shows you compressive forces, and just think, it's internal reactive, so it's opposite to compression, so therefore it's tension. Okay, so let me go through Bose notation. So this member here is DA, and that's because you've got to read it clockwise. This member here is AE, and this member here is ED. And you call that joint AED, or you can call it DAE or EDA, it doesn't matter. I've called it here AED. And so relative to this joint here, this member is AE. But relative to this joint, because the sense changes, this force here is EA, because you've got to read it clockwise. And can you see what Bo did? He made up this nomenclature to account for the change in sense of these forces relative to the joint. So I'll just go through that again. This relative to that joint, this member is AE, and you can see it on the force diagram down here, it's AE, but relative to that joint there, this member is EA, because you've got to read it clockwise. And you can see on this diagram here, that's EA. Okay, so I'll just go through this, and then I'll go through the Maxwell diagram. Notice that I've numbered all these joints here. So that's number 1, that's number 2, number 3, number 4, and number 5. And that will help us work out this Maxwell diagram, the sensors on the Maxwell diagram. Now, the joint that you've got to start with is a joint with no more than 2 unknowns. So see this joint here? We've got 1, 2, 3 unknowns. This joint here's got 1, 2, 3 unknowns. This joint here's got 1, 2, 3, 4 unknowns. And this joint here has got only 2 unknowns. And this joint here has got only 2 unknowns. So you can start with that joint or that joint, and they're always the reactions. You should be able to work out the reactions now. Now, both these reactions are vertical, even though a pin joint can take any reaction in 360 degrees. But these 2 reactions here have to be vertical because the external forces are both vertical. If you had an inclined force out here, you would have to have a horizontal component on this pin here. No horizontal component on a roller because it'll just roll it. So let's start with analysing this joint here. And you've got to make sure that you transfer these angles. You can see that it's 60 degrees there. Sometimes, if they don't give you any sizes here or any angles, it's always 60 degrees, and you just take the length of the members as 1 if they don't give you any size, but generally they'll give you sizes. I've only told you here that this is 60 degrees, and that implies that everything is 60 degrees. So some of the moments about the pin, and you get RL is equal to 220 kilonewtons acting up, and some of the vertical forces, and you get 95 acting up. So 220 plus 95 has to equal 250 plus 65 when you add the 2 together. Let's analyze this joint here. So the first, you can start with you have to start with the known force. RL is 220, and I've used a scale of 1 millimeter equals 5 kilonewtons. And so you draw that line vertically, and make sure you get it vertical. Compare those forces there to get this line vertical. Don't use the side of the page because this diagram might be inclined, but it won't be in the HSC and in the papers that I set. So that's a vertical line, and so you make that a particular length according to 5 kilonewtons equals 1 millimeter, just by 220 by 5, and that will tell you how long that is. You put your cents on it because you've got the cents given to you there, and then so you've marked the ends of it, and you call this force going clockwise is dA. So you use capital letters for Bose notation, but on the force diagram you use lowercase. So write that in as dA. Now you've got A here, and so the next force is AE, and we don't know whether that's going up or down, but we know that it's going through A, and we know that it's 60 degrees. So you just draw a line through A at 60 degrees. We don't know how long yet, and that's all you can do with that. And then you come down to the next force, which is ED, and you know that is horizontal, and it's got to go through D. Just put a horizontal line there where these two lines meet. That is E. And because the sense is going vertically up on this, you've got to follow the senses all the way around the diagram according to that, because the joint is in equilibrium. And so this sense goes down towards the joint. So it's right the way I've put it there. And this one goes away from the joint. And so it immediately tells you that that member is in compression and that member is in tension. And you just use your scale to work out the magnitude of that. And you can see that it's 254 kilonewtons. I should have put the units there, and it's in compression. And this is 127 kilonewtons, and it's in tension. And so you've totally analysed that joint there. Now, remember I said that you can't analyse this joint because you've got 1, 2, 3 unknowns. But now we know this one because we've worked it out there. We know there's 254 kilonewtons, but the sense has to be the other way because the force has to be equal but opposite to the force down there to be in compression, to put this member in compression. So we can start with that straight away. And and this is joint 2. And so I'll go through this, and then I'll go through how I've put it all on one diagram, this particular one. So you've got to start with that force there. You go around, and the first one you know, going clockwise, you start with that one. That's the way I always do it. So it makes it easy. So we start with EA, and that's exactly the same as the EA there, but over here it's AE. So you go EA up there, make sure it's parallel, it's 60 degrees. This force here is AB. It's got to go through A, and so it goes vertically down, and it's 250 kilonewtons. Divide by 5, and you'll get how many millimeters it is. And so AB goes down. Make sure you put your B there and put your sense there. And then the next force that you come to going clockwise around here is BF, right? And that's horizontal, so we don't know whether it goes to the left or the right. And that's all you can do with that. Just put it in, and we don't know, and I should have drawn it out there to show you we don't know where it goes. So you come to the last force, which is FE, and we've already got E, and we know that that angle is 60 degrees. So you put a 60-degree line down there, and that will be F there. All right, and I haven't put it in there, so I should have. I've forgotten about that. So that should be FE. Then we know that the sense goes up because it's got to be equal and opposite there. And this one has to go down that way because it tells you there. And then so this one will go that direction, that'll go that direction. Measure off these lengths here, and you've got the magnitude of the force in those members. Okay, so we've found the force in that member and that member, and over here at this joint, joint number 3, we've got 2 unknowns now. We already know that one because that is BF here, and it becomes FB over here. Now, before I go on to these two last joints, let me show you on this Maxwell diagram, and don't forget, you don't have to use the Maxwell diagram. If you want to analyze, which you'll have to, the forces in all members of your truss that you have to actually build out of balsa and test to destruction for assessment task 1 that I'll explain to you when I see you. I think this is the best way of doing it, Maxwell diagram, but if you want to use individual diagrams, that's fine. So let's go through joint AED. Okay, so here we have A, E, D. So the first thing you do is that you draw in DA, like I've done over here. Put your sense, and see I've put 1 there because that's a sense relative to joint 1. And then this comes down, there's sense relative to joint 1. And then that is AE, and then this is the sense relative to joint 1 there. So there's our force diagram, exactly the same as that one. But the next, when we analyze this joint here, we remember for this joint, this force is AE, but for that joint, it is EA. So this is member joint number 2, and that's the sense of the force here going into the joint. It's in compression, and it's EA. So we've got EA going. Then the next force is AB, which is 250 kilonewtons, 25 tons, acting down here, and that is AB. And so there we've got B there, and see the sense there for joint number 2 is coming down here. It's coming further than the joint number 1. So that's joint B. Then the next force is BF here, like that one there, BF. So there's BF, and that's going to the left because that's joint number 2, but we don't know that yet. And so we don't know where BF is. And so we know that FE, see this member here, that's FE. We're going clockwise, remember, and it's got to end at E. And so you just draw a 60-degree line down there and you find F there. And you can see that that force is going up relative to the joint because that's joint number 2. So we put the sense on that going up, and we, and we know that the next one is equal and opposite down there, and we can put that force in straight away. So you see what I've done, I've incorporated that diagram onto this diagram. And it gets a bit confusing, but once you number the joints, it will help you. For example, joint 3, there's joint 3 there, and we know that FB is going in that direction, and here is FB, right? And so we know that straight away, relative to that joint, it's going in that direction. And so this one here has to be equal and opposite. And so that member is in compression. So let's see this joint here, or the diagram, the force diagram, it's too small. You know the rule about force diagrams. If you join your thumb and your second finger to make a circle, if you can see your force diagram in that circle, it's too small and you may not get within 10%. So make sure that you have a scale that will be sufficiently big enough to be accurate. So we're on to, now this is joint D, E, F, G, C, right? So we've got, where I came down to this joint here. So that's D, E, F, G, C. So that's the name of that joint number 5. And so I'm going to start with this 65 kilonewton force there. And you've got to go and then read it clockwise. And so that is CD. So I've put CD in there. That's 65 millimeters. What's that? That's 5. It's only 13 millimeters long if you're using this scale. And so that's CD. Now the next force is DE, and DE comes out here. Right? And we already know what DE is, because there's DE there. We've already worked that out. It's 127. So we can draw that to scale. We already know what EF is. And this will be EF. There it is there. That's 35 kilonewtons. So that's EF. And now we come to the last two forces that we don't know. And that is FG and GC. So we know that FG has to go through F. So you draw a line in at 60 degrees. We don't know whether it goes up or down yet. But see, this last force here is GC, and it's got to go through C, so we know where G is there. And then you scale, put all the sensors in correctly, same direction all the way around the force diagram, and then scale that off, and then scale that off, and you'll be able to work out what the magnitude is in these two forces here. Now you can see that FG is going up, so you immediately put that force relative to the joint, and this one will come down here like that. So that's in tension. And then GC relative to that joint, going clockwise, is going to the right. And so that goes to the right relative to joint 5. And that goes in there like that. And so you can see that's in tension. And the last thing that we've got to do is to find the force in that member there. And so you know what RR is. So it's 95 kilonewtons. And that force there is BC. So you draw BC, 95, which would be 13 millimeters going up. And then reading it clockwise, you've got CG. It's got to go through C. And we already know what that force is there because we've worked it out here, and that's 55. And then this next force is GB, and it's got to go at 60 degrees down through B. And so you can work out what that force is, and see it's going down to the right. So that will have a force of compression in that member. Okay, and so what I've done here down at the Maxwell diagram, I've made this diagram much bigger, and this is a much more accurate diagram than these little ones here. But these answers are pretty correct because I did them using analytical methods. that you'll use at university, probably, because universities don't like graphical methods, even though they're very much easier to understand if you're not a mathematics head. So let's analyze joint number 3 here, and on this diagram, and that's the only one that I'll do, because otherwise it could be confusing you. So I jumped from that joint to that joint, and then I'd already found those forces there. But I'll just analyze this joint using the Maxwell diagram. So all I know is that force there. And so I know that that force is BF, but relative to this joint, it will be FB. So here we have FB, we know that, and that's going to the right, like that says there. And we've already found BF on joint 2. And so for joint 3, we use FB, it's going to the right. And then the next force coming is this one here, which is BG. And so we just draw a line at 60 degrees through B. We don't know whether it goes up or down. And then we have to leave it there. And then we have to go to this last force, which is GF, which has to go through F because it's GF. And so you just put a 60-degree line up there, and where these two lines meet, that's G. And so this is for joint 3, so that goes to the right, that goes up to the left, and then this one, GF, for joint number 3, goes down, and you've got exactly the same as what we worked out here. So I hope you understand that. I can understand that you can get confused with this, but individual diagrams, you are less confusing. The only disadvantage with this is that you have to draw that line twice. And here you just use those existing lines. And so that's called the Maxwell diagram. Now, make sure that you realize that you'll never be asked to do a joint analysis of a truss or find the members in the truss in any particular way. It's up to you which way you do it. Next week, we'll be doing method of sections, where you can pick a particular member out and find the force in the member without doing all of these little diagrams. And finally, remember that you won't ever be asked in the HSC to find all the forces in a truss, because it will take you an hour or 3/4 of an hour to do all of this, and also it's repetitive. And the only time you'd use method of joints is if you're asked to find a force which is fairly close to a joint or a reaction. Some students I've noticed when I've been marking, if they're asked to find a force in this member, all you have to do is do that force diagram and that force diagram, and you can find the force in that member. But I'll be showing you how to find the force in an internal member by using the method of sections. But as I said, it's up to you to do it whichever way you like. Okay.